All right, so I thought we'd do a problem about polarity. And so I'm asking, are the molecules NH3 and pH3, are those polar or nonpolar? And so how are we going to figure that out? Well, we need to know the shape first, okay? So let's start with pH3. And we can actually do these kind of side by side. So I'll do pH3 on the left, NH3 on the right. So valence electrons first, right? 5 for phosphorus, it's in group 5, and 1 for hydrogen, so that's going to get me 8 valence electrons. Turns out these are isoelectronic, meaning they have the same number of valence electrons, so they both have 8. Okay, central atom has to be phosphorus and nitrogen respectively. Hydrogen never can be the central atom. And if you go through this, these are going to be the Lewis structures. Okay, and so let's see if this makes sense. We just connected them with 2, 4, 6 single bonds, and then added our 7th and 8th valence electron as a lone pair on both of them, and that gave an octet structure, octet rule being satisfied for both the phosphorus and the nitrogen. Steric number for both of them is going to be 4. Why is that? There's 1, 2, 3 bonding sites, and there's 1 lone pair. That's a total of 4 bonding sites plus lone pairs. That gets you a steric geometry for both of them of tetrahedral. Okay, now what about the molecular geometry? Remember, the molecular geometry is the same if there's no lone pairs on the central atom, but there is a lone pair on the central atom. There's 1 lone pair, so that's going to mean it's a tetrahedron with one of the vertices removed. That is called the trigonal pyramidal structure. So both of them are going to be trigonal pyramidal structure. You can see because they're isoelectronic, these are essentially the same. The only thing that changed was one has an N here and a P here. Okay, so this is the tripod type structure. So now we're asked, is it polar or nonpolar? Finally, we're able to sort of get to the gist of this because we need to know the shape of this molecule to see if we do have a polar bond. It doesn't necessarily mean the molecule is polar. The dipoles could cancel each other out if we have a tug of war. For example, if we have a dipole, a tug of war happening to the left and happening to the right, net, we're going to have no dipole, right? And so that, even though we might have polar bonds, so an example of this would be like CO2. CO2, that's a Lewis structure, okay? And you have a dipole, oxygen is more electronegative, pulls, oxygen's winning the tug of war to the right that way, but this is a linear molecule, 180 degrees, okay? And the other oxygen is pulling the tug of war to the left, and so net, you have nothing. So this is actually a non-polar molecule, even though it has polar covalent bonds, okay? But that's an aside. Let's go to this. That's why we have to come up with the shape, okay? Phosphorus and hydrogen. If you look up the electronegativity, how do we figure out if we have a polar bond? We have to look up the electronegativity, right? Electronegativity of phosphorus is 2.2. Remember, I'm going to always give you the electronegativity. There's a chart that I'm going to give you, okay? Electronegativity of hydrogen is 2.1. So the delta electronegativity there is just 0.1. 0.1 is less than 0.4. That was our threshold for whether something was polar covalent. If it's greater than 0.4 and less than 2, we call that polar covalent. If it's greater than 2.0, we call that ionic. If it's less than or equal to 0.4, we call that nonpolar covalent. I mean, yes, slightly polar for phosphorus. It's winning the tug of war slightly, but you know, chemists just call that nonpolar because you can't really even see that in most experiments, okay? So there's no positive or minus charge here. There's no real, it's an equal tug of war. So definitely this molecule is nonpolar, pH3. Why is it nonpolar? It's made up of nonpolar bonds. You have to have polar bonds to have a polar molecule. If you have polar bonds, that doesn't necessarily mean you have a polar molecule. Right? That was the discussion about this, the molecules, the polar bonds canceling out. Okay, NH3. electronegativity of N is 3.0. So we already know for hydrogen, so the delta electronegativity for an NH bond is 3.0 minus 2.1, that's 0.9. Ah, that's greater than 0.4, less than 2. That is a polar covalent bond. So now, nitrogen is winning the tug of war substantially enough. So we put a delta, that's a lowercase d in Greek, okay? Delta negative for nitrogen is the more electronegative one. And all these are going to have positives. The hydrogens are losing out on the tug of war. And we can draw an arrow. And we draw an arrow in the direction of the electron density. So we have these three arrows. And now we have to think, are these three arrows canceling each other out? Is this a symmetrical molecule, a totally symmetrical molecule? And the answer is no. And if you can kind of think about this, right, this is a tripod, right? And so net, all these are, you have this tripod, and they're all pointing towards the nitrogen, towards the top of the tripod. And so net, you're going to have, you know, one big dipole pointing just straight up towards the nitrogen. So definitely, this is a polar molecule. Okay. So that's how you would figure this type of problem out.